Far from the sun, beyond Earth, beyond planet Mars and the asteroid belt, giants roam the outer solar system. The Jovian planets and their moons, worlds that until recent years cloaked their mysteries in the great distances between us.
What used to be true is that we knew about the 8 other planets. Some we could see well through the telescope, others were nothing more than pinpoints of light. We also knew that many of these planets were surrounded by moons, by satellites. Suddenly, as we sent our robot armada out to explore the solar system, we discovered that these little pinpoints of light were each worlds, and each of these worlds was different.
We're extremely lucky to be alive at this time because for the first time in human history, we were able to go out and take our cameras and our eyes and our senses and go out and explore the backyard, which is our solar system. Voyager enabled us to do that. It was the first time we were able to explore basically the entire outer solar system in one shot. And to be part of that was an amazingly exciting time. So many things were discovered. It got to the point where the thing that we started to expect was to be surprised. The most profound things that we discovered were things that were totally unexpected.
Our journey of discovery began when the first of 2 Voyager spacecraft encountered the colossus of the solar system.
Jupiter was recognized by the ancients as a planet, that is, as a wanderer amongst the background stars. And it was a prominent wanderer as well, 4th brightest object in the sky. After that, you couldn't say much about it unless you looked at it with a telescope.
Jupiter is an interesting planet because it is made, except for its very heart, almost entirely of gas and liquid. If you were to try to land on Jupiter, you wouldn't. You'd just sink in and in and in and in.
Jupiter is basically a large ball of liquid hydrogen and helium under tremendous pressures. And instead of being cold when a gas is liquid like it is on the Earth, the pressures at Jupiter are such that it's hot liquid gas.
In fact, most of the planet is rather uniform in composition, rather similar deep down inside the planet as it is near the surface of the planet. Of course, as you come up into the atmosphere, it becomes cold enough that you form clouds. And those clouds even have some color, and that's why we can see these differences from one place to another, such as the bands.
And what's interesting is that this enormous planet, where 11 Earths can fit side by side, whips around, turns on its axis in only about 10 hours. So think of this huge cauldron of gas and liquid whipping around so fast, there's an enormous amount of what we might call, with the technical name, sloshing. And we see the sloshing patterns in the atmosphere of Jupiter as enormous storm system, large bands of violent storm activity.
The rotation rate of a planet has a really strong effect on what the clouds are going to look like. The Earth is sort of a medium-fast rotator, and so we get storms that look like hurricanes and cyclones and tornadoes, very characteristic spirals. When you take a planet and make it rotate fast, like Jupiter, it's rotating in 10 hours, and it's a whole lot bigger, these speeds get to be really appreciable from rotation. So the patterns that would have made cyclones on the Earth turn into belts and zones on Jupiter.
Through the eyes of Voyager, we could see the violent motion of these immense bands often twist the atmosphere into colorful swirls of gas, including one which has captured our imagination for centuries.
As telescopes improved and observers grew more careful and more disciplined, they began to see more and more detail on Jupiter. They could see that there were bands on the planet, and they could also see within one of these bands a very peculiar feature. It was kind of reddish in color, and so astronomers, with their incredible powers of imagination, decided to call it the Great Red Spot. And the next problem was figuring out what it was, and of course nobody knew.
The Great Red Spot is a truly remarkable feature in the atmosphere of Jupiter. It is considerably larger than the Earth itself in size, and it has existed for many centuries now, although the color has changed over time. But it is a remarkably persistent feature, and we now know from more recent work that it has a circulation associated with it, which is very much like large storm systems on the Earth.
This enormous storm has been observed raging unabated in the atmosphere of Jupiter ever since we first saw the planet through a telescope in the 17th century. The reason we think we now understand, here on Earth, tropical storms spend their energy by doing something terrible like destroying a city in Florida or devastating a part of the coast of the Gulf of Mexico. But there is no dry land on Jupiter where a storm system can spend its energy, and so the storms continue and continue for centuries and perhaps millennia.
After giving us our closest views ever of Jupiter's violent atmosphere, Voyager turned its instruments to the planet's vast magnetic field.
We didn't know before we went with spacecraft to the outer solar system whether we would find magnetic fields at all of the outer planets. Jupiter, we knew, had a magnetic field even from measurements from the ground. The radiation belts at Jupiter make enough radio noise that they were discovered in the 50s by radio astronomers from the Earth. It's like a huge bar magnet deep within Jupiter. It controls, if you will, a region of space around Jupiter that's larger than the volume of the Sun itself.
Jupiter's magnetic field is produced, we think, in much the same way as the Earth's field. Deep within the planet, we think that there is a liquid metal that is churning over, creating a dynamo, which in turn produces this very large magnetic field. The liquid metal, in the case of Jupiter, amazingly enough, is hydrogen, and that material, which is called metallic hydrogen, is the conductor for the currents that are responsible for Jupiter's magnetic field.
With its powerful storms and huge magnetic field, Jupiter provided Voyager with an awesome spectacle. But the real surprises came when the probe turned to the planet's astounding collection of satellites. 4 centuries ago, Galileo pointed his telescope to the sky and for the first time in history viewed the moons of another world.
He saw around Jupiter, associated with Jupiter, 4 other objects, 4 small stars. He first called them the Medicean stars. We now call them the Galilean satellites, after Galileo's discovery of them. But these are the 4 largest moons of Jupiter. And of course, he had no idea how many more of those moons would be found around Jupiter or around the other planets in the solar system.
As you go out from Jupiter, you encounter Io, a rocky moon, Europa, which also has a lot of rock, but also has a layer of ice covering it, and then the 2 big ice-rich moons, mostly made of water, Ganymede and Callisto.
The most interesting of all of them has got to be Io. That satellite contains no craters at all, and yet an old surface in the solar system should be covered with craters because of meteorite impacts. So when we see a surface where there are no craters, we know that something has erased the craters.
So when we got there with Voyager, we were sort of thinking volcanoes, but we were thinking ancient volcanoes. I mean, what amazed us was that we were actually seeing these things popping off in front of our eyes when we got there. Our first reaction when we saw these things was, wow, they're actually erupting right now.
In Io's case, the mechanism for the volcanoes was quite different than the mechanism that causes the volcanoes on the Earth, but the volcanoes are there nevertheless as a geological expression of the same phenomenon, the release of heat from the interior.
Io has the misfortune of being the closest large moon to Jupiter. And as such, it feels Jupiter's enormous gravitational tug. In fact, the pull of Jupiter is so great on Io that Io's insides are literally churning all the time.
And because of that continual flexing, heat is produced, just as if you take any object like a credit card or any other piece of material and bend it, you can feel a small amount of heat being produced in that object. The spectacular consequences are in the form of volcanism and geysers, material heated so severely inside Io that it rises to the surface and flows out on the surface. Flow of liquid rock and sulfur and geysers of sulfur dioxide.
Io is resurfacing itself. It's different month to month, year to year, because through all these volcanic holes, the insides of the little moon are coming out. You cannot make a map of Io, for example, because it will just be different the next time you look.
If you had people living on Io, and I wouldn't recommend it because the radiation is so severe there, but if you did have people living there, they wouldn't get a weather report because there's no atmosphere, there's no weather. But you get a geology report. I mean, mountain building to the east and volcanic floodplains to the west, you know, and that kind of change occurs on the scale of human lifetimes.
The next moon after Io, as we go out from Jupiter, is called Europa. It is a moon about the size of the Earth's moon. It is covered with water ice. We believe that the ice may be only 10 kilometers thick and covers an ocean of water underneath.
Europa's surface is almost entirely devoid of impact craters. This tells us that the surface is relatively young. That is, it may be as recent as just a few hundred or even a few thousand years old.
What's making that surface renew itself? It could perhaps be the same mechanism that drives Io to be a young object. This tidal heat energy works its way to the surface. In Europa, perhaps it's the same process at a reduced level of activity that causes the surface to slowly evolve.
We think that because it is so bright and because it is crisscrossed by features that may be due to the flexing of the ice, that perhaps there is material flowing out occasionally on the surface of Europa, that perhaps Europa is even in a certain sense volcanically active, except that in this case, instead of liquid rock, it is water that is flowing onto the surface. Ganymede is the largest satellite, both of Jupiter and indeed in the entire solar system. It is at least half water ice. The remarkable thing about Ganymede is that it has two kinds of surfaces. It has a brighter grooved surface, which has somewhat fewer craters, and a dark intervening surface, which is more heavily cratered. We believe that the less cratered, brighter terrain is younger and apparently was produced by flow from the interior.
They're formed by tectonic forces within the satellite, splitting the crust, causing it to open up with fractures, perhaps having material then flood up from the interior, in this case probably mixtures of ammonia and water ice that had been heated. So Ganymede had a complex history early on. It's probably mostly quiescent now with a hard frozen crust.
The outermost large satellite of Jupiter is called Callisto, and it is very similar in composition to Ganymede, but remarkably it has none of the resurfaced material, none of the grooved, less heavily cratered terrain that Ganymede has. In fact, Callisto is one of the most heavily cratered objects in the solar system.
Callisto is, if you will, a large, dirty ice ball with lots of holes in it. People, before we started exploring the outer solar system, generally tended to think that most of the satellites in the outer solar system would look like that. It's an ancient surface, completely covered with craters every place you look.
And perhaps the most interesting of these is Valhalla on Callisto. What we believe happened, and we don't know for sure, is that perhaps 4 billion or so years ago, an enormous chunk hit this moon Callisto. The impact of that chunk was so great that it actually melted the frozen ice.
In addition to revealing the amazing diversity of Jupiter's moons, Voyager discovered a pale ribbon of debris circling the giant planet.
We used to think that only Saturn had a ring system, And up until the Voyager spacecraft, that seemed to be the case. But when the spacecraft started visiting the outer solar system, and when other ground-based measurements started looking for rings in the outer solar system, we discovered that all of the Jovian planets have got rings. They're not the same kinds of rings around all the planets, but it is a common property of Jovian planets.
There were no suggestions from Earth-based observations that Jupiter had a ring system at all. When the Voyager spacecraft flew by, a very important set of photographs at the precise location where one might expect rings to be showed that Jupiter has a small ringed system. And so that was a spacecraft discovery that goes to Voyager.
Leaving Jupiter, its moons, and faint rings behind, Voyager journeyed on to the next giant in space, to the ringed planet and its multiple moons, each with features we did not expect.
Well, Saturn, the second of the giant planets as we go into the outer solar system, in many ways is a slightly smaller relative of Jupiter. It's also composed almost entirely of hydrogen and helium with some heavier gases.
When we look at Saturn, we see clouds in the atmosphere, which, just as with Jupiter, are made of ammonia crystals, tiny crystals forming cirrus clouds high up in the atmosphere.
Motions in the Saturn atmosphere are very similar to those that one sees in Jupiter's. That is, very large weather systems by terrestrial standards. They're large cyclonic features, if you will, immersed in large zonal wind patterns that form these latitudinal belts and zones that you see on the giant planets. There's no equivalent of the Great Red Spot on Saturn, but there are a number of not-so-great spots, if you will, or modest spots.
The atmosphere of Saturn has far less cloud structure than Jupiter. It seems somewhat bland, and we're not quite sure why that is, but certainly there is more scattering of the sunlight, and perhaps there is less of the material that produces the color on Saturn than on Jupiter.
Although quite different from Jupiter in appearance, Saturn holds a similar mix of internal elements.
Well, Saturn's interior probably is quite similar to that of Jupiter's. That is, as you go down through the cloud layers, you'll run into more compressed, hotter gases until the gases become, in effect, liquid under very high pressure, even though they're at high temperature.
Saturn, like Jupiter, has an interior that we think is metallic hydrogen, this state of hydrogen where the molecules are squeezed so close together that they form a metal. And this indeed is the region of Saturn that is responsible for Saturn's magnetic field, as well as for a large fraction of its mass.
While it has much in common with Jupiter, Saturn has one feature that sets it apart since it was first seen through a telescope nearly 400 years ago.
The telescope told Galileo there was more to this planet than met the unaided eye. He saw the disk of Saturn, but there were a couple of things sort of hanging on either side of it, sort of like a couple of ears stuck onto the disk itself, and he didn't know what that was. We now know what he was really looking at were the rings of Saturn.
When they were first seen, people did not know what they could be. It was even thought that it might be a solid object forming a ring around Saturn. Later, it was realized that that was impossible, and now we know that the rings of Saturn are made of a very large number of small particles, apparently mostly made of water ice.
What would it be like to be inside the rings of Saturn? Well, it would be the most incredible snow and hailstorm, but with much larger chunks of snow and hail than we're used to. There would be space in between them, but you'd be surrounded by billions and billions of individual snow and ice balls.
There may even be chunks of material in the rings of Saturn that are the size of houses and certainly the size of basketballs. But a lot of it indeed is in small particles, the size of pebbles, marbles, all the way down to fine dust.
It's an incredible system, consisting not just of a ring or even a few rings. Voyager revealed that there were thousands and thousands of ringlets and mini-rings within each of the major ring systems.
Not only did we find these concentric ring features in Saturn, we also found these oddities. We found these eccentric rings, rings that weren't circular. We found rings that, that appeared to change with the influence of the moons on the outside. We found these spokes, these wispy features on the rings that you could see from millions of kilometers away, things we really didn't expect at all.
The surprising structure of these luminous rings offers clues to their origin.
One of the ongoing debates about the rings of Saturn is how old are they? The thought was they must be relatively ancient. Studies of the dynamics of the rings since we've gotten the Voyager data suggest it's very difficult to keep the rings as they are now for very long geologically.
These are fairly recent occurrences. So the probable cause is some sort of mini catastrophe that could have occurred in recent evolutionary history, the collision of an asteroid or a comet with one of the moons of these objects.
And we do just happen to be fortunate that some event not too long ago in geological history produced the rather spectacular rings we see around Saturn now.
Beyond these spectacular rings, our spacecraft reconnaissance continued with the many moons of Saturn. Soon, the photos and data began to tell the story of a diverse collection of complex and sometimes mysterious worlds.
One of Saturn's many satellites is called Titan, and it's an especially large one. It's larger than our own moon, for example, and it's distinguished in that it has a rather dense atmosphere.
It has an atmosphere of nitrogen, made of essentially the same thing as most of the atmosphere of the Earth, only it's very cold nitrogen. At the surface, the temperatures are equivalent to that of liquid nitrogen.
But Titan's atmosphere also has a little bit of organic material in it, and in particular it has the gas methane. Now when sunlight shines on a methane-rich atmosphere, organic chemistry takes place. And in the case of Titan, a kind of a haze or an organic smog is formed by the impact of solar ultraviolet light on this nitrogen and methane atmosphere.
When the Voyager spacecraft got to Saturn in 1981, we found that the atmosphere was considerably thicker than some people had thought. If you were standing on the surface of Titan, you probably couldn't see Saturn through the atmosphere. From the Earth, we've sent radar beams out to Titan, gotten radar returns from Titan, so we know it's got a solid surface. It's probably frozen ice, possibly with the liquid and solid hydrocarbons raining down slowly from this smoggy, hazy atmosphere.
There may be, therefore, a large accumulation of organic material on the surface of Titan. It may not be too different from some of the conditions on the early Earth, for example.
It's possible that part of the surface of Titan is covered with lakes of liquid methane and byproducts of methane. Whichever way, the surface has to be something quite fascinating, something different from anything we have seen before.
Enceladus is another interesting moon. It's a satellite of Saturn. Some of the regions on Enceladus are old and they're battered with craters, but some of the regions are really quite smooth, and that means there has to be some kind of geological activity in the recent past on Enceladus that has erased some parts of the surface.
It's far too small to have enough radioactive elements in it to melt easily and produce these types of volcanic features. And so we believe it also is getting some amount of tidal energy from interactions with the other moons in Saturn, but the numbers don't work out as well as they do for Io, and the theoreticians are still working on that one.
One of the smaller moons of Saturn is called Mimas. Mimas is an icy object made mainly of frozen water, but it has this very special characteristic in that it shows a very, very large crater.
This crater is the largest crater, the largest impact that this little moon could have sustained without breaking apart. In fact, the crater Herschel on Mimas is so large that the back of the moon, 180 degrees away, is actually cracked. We believe that this was an instance in which, if something a little bit larger had hit, the moon would have cracked into 1,000 pieces, and Saturn might have another ring system.
The Voyager missions brought us a parade of unexpected discoveries about these moons, rings, and the mammoth planets they circle. Discoveries that raised new questions and left us yearning to know more.
We really want to go back and get a closer look and find out what the geological processes are. Is there silicate eruptions going on Io, or is it all due to sulfur compounds? The peculiar terrains on Ganymede, what has been causing that? Is the crust being replaced by this younger-looking material? We didn't get a close look at Europa at all, and we'd really like to understand its peculiar structures. Around Saturn, we want to go back and really understand the rings. We want to understand the dynamics in the atmosphere and get a closer look at the moons.
We've only just touched the surface, if you will, of beginning to understand these places. They're, in effect, each little planetary systems in their own right. And if you think about it, the spacecraft emissaries that we've sent there have spent literally only a few days in their vicinity, doing a quick reconnaissance and then going on further out into the solar system.
From Galileo's first glimpse of Jupiter and Saturn to our latest views from Earth and space, we continue the quest to understand these giants of the outer solar system.